Hello, welcome to the 10th lecture in the series of Tribology for the Beginners. This is a lecture on polymer wear and part 1. In the last lecture, we have discussed wear in general and wear of metals in particular. But polymer wear is quite complicated, more complicated than metallic wear. And hence there are a lot more parameters to be considered and more details have to be given. That is why we have divided this lecture into 2 parts, part 1 and part 2. Before we go to the next slide, I like to give you some introductory talk on this. That is, polymer wear is a combination of adhesive, abrasive, and fatigue wear. We'll discuss this in more detail. But because the mechanism of polymer wear is difficult and complicated, so we discuss the adhesive and abrasive wear part in part 1. We'll also be developing a model to predict the wear of polymers. So let's go to the next slide, where we talk about why polymer wear. In fact, polymer has attained a very special place in engineering because of many reasons. And some of them they're lightweight, they're flexible, they're easy to machine, which is a very important thing in engineering. And some of them are self-lubricating, and they have got favorable mechanical properties like strength to weight ratio. There are many other properties, and we'll discuss this as we go ahead. Now, next thing to discuss is that there are very few polymers which have got favorable friction and wear properties. And this is why we choose mostly some of the following polymers in engineering. PTFE is well known. Polytetrafluoroethylene is a very well-known polymer. It is easy to machine and it wears, but it's useful for engineering. Nylon is also well known. PEEK, polyether ether ketone, is also an important polymer, which is now well used in biomedical applications. For example, in joint prosthesis and other developments. HDPE, high-density polyethylene, and ultra-high molecular weight polyethylenes are well known for making prosthesis, joint prosthesis, especially hip and knee joints. PU, polyurethane, is also a biocompatible polymer, very useful. PI, polyamide, is also very useful. Epoxies, we all know, and phenolics is also well known for their engineering uses. So with this, we go ahead with the friction and wear properties. Now, as we said earlier, that wear mechanism of polymers is complicated, more than the wear mechanism of metals. And this is due to its dependence on many factors. Metals also have many factors, but polymers have got much more factors to be considered for explaining the wear mechanism. First of all, molecular orientation. To talk about molecular orientation in engineering, we normally discuss crystallinity and amorphous. These two types of polymers have got different wear mechanism. Crystallinity gives very close orientation of the molecules, and hence they'll wear less. And amorphous don't have that, so they do wear more. Among the physical properties, most polymers have got high molecular modulus of elasticity, low conductivity, and low melting point. So these are points to be considered because for example, low conductivity and low melting point would lead to melting wear if the contact temperature due to rubbing rises beyond a certain level. So these are the points to be considered for polymer wear. Now, counter surface roughness and hardness. Both these are very important because harder the counter surface and rougher the counter surface, they'll abrade the polymer more. So obviously we have to take these two factors into consideration. Surface energy. Surface energy, as we have discussed in earlier lectures, is the excess energy in the surface due to the molecules which are not bounded by other molecules. And obviously, they do affect the adhesive wear. Adhesive wear is not so clearly seen in normal polymer wear because polymers usually are abraded or fatigue. But adhesive wear comes during abrasion. We'll see that later on. As we said just now, contact temperature rise is also a very important factor in discussing polymer wear mechanism because it will affect the property of the material and how it wears. As we also said that it will be melting wear may occur if the contact temperature rise is high. Load, speed, and other operating conditions, of course, would affect the wear. This is also true for metal wear, but it is also important for polymer wear. Environmental condition affects polymer wear. For example, carbon-filled PTFE would wear more in air or oxygen atmosphere than in nitrogen and helium atmosphere if the humidity is comparable. So these are some of the points that we got to remember, we have to remember before we proceed to analyze the wear mechanism of polymer. Now, wear, as we discussed before, is a progressive loss of material during relative motion between contacting surfaces. This is an easy statement, but there are many more things happens while the two surfaces are rubbing each other. And we also said earlier that polymer wear is a combination of adhesive, abrasive, and fatigue wear. Just to give you some example, experimental example, in the early stage of sliding against a rough surface, polymer will be abraded, obviously, understandably, because of the rough surface. But as the surface is slid repeatedly, the sliding wear and the abrasive wear rate will fall because there will be a transfer layer deposited onto the polymer surface. This transfer layer, uniform transfer layer in polymer during rubbing is a very important point to be considered. Two examples of transfer layer are shown here experimentally. The first one is the HDP transfer layer, which looks like an abraded surface, and this is a lumpy transfer. This is a straightforward transfer, and this is a lumpy transfer. So these do make the difference in polymer wear. Next, while the transfer of polymer layer takes place in the opposing metal surface, then the adhesive interaction contributes to wear. So the point is this, that while the rough surface is rubbing onto a polymer, the transfer layer onto the metal surface would reduce the roughness and hence the abrasion or abrasive wear loss will fall. And there, obviously, the adhesion or adhesive interaction will contribute to wear. And this is where the adhesive wear factor comes in. Now, we also said that the fatigue is an important issue in polymer wear. And this usually happens at low rubbing severity. By rubbing severity, we normally say that mu W is the frictional force and V is the velocity. So it denotes the energy or frictional energy transfer or frictional energy developed at the surface. And at the low rubbing severity, at the smooth surfaces, fatigue wear is likely to occur. And that even at the elastically deformed asperity contacts. See, when rubbing takes place between the two surfaces, the roughness is important. But it's also more important to understand that what kind of deformation takes place. When a hard asperity digs into a polymer surface, then it must dig plastically. Otherwise, abrasion will not take place. But that will not lead to fatigue. For fatigue wear to take place, we need to consider the elastically deformed asperities, or when the hard asperity peak deform the elastic polymer surface elastically. So we need to distinguish between the elastically and plastically deformed asperities. This we'll do later on. Here we give some examples of melting wear. As we say that the low specific heat, low conductivity, and low melting point of polymers lead to melting wear. And this may occur to PTFE, as we see here. PTFE will not have melting wear. PTFE usually the low rubbing severity will have cracks, and this is these are the cracks which leads to fatigue wear. But PP will have molten layer, and so would the PP pin that we did some experiment in pin on this surface. It can be seen that the edge of the pin has been molten, and molten layer will come off, leading to molten wear. So these are some of the examples of molten melting wear and fatigue wear. Now we start looking at how to model or an approach to predict polymer wear. Because it's a complicated process, many authors have tried to develop models for predicting. There are two types of predicting mechanisms of predicting tools. One is empirical equations, that is the analytical approach. Now, empirical equations are basically developed by looking at the experimental results and fitting them to certain empirical relation. Ratner et al., 1964, probably one of the first empirical equations developed, looks like this. V is the wear volume, which is equal to K. K is a wear constant. It is a little different from wear constant for metal. We'll see how later. K mu is the friction, coefficient of friction. W is the load, and L is the sliding distance, divided by HS epsilon. H is the hardness. This we have in metal also. S is the rupture stress, because here rupture of polymer as it is abraded is important. That is probably the third stage of abrasion, where the chunk of material comes out, and epsilon is the rupture strain. So the denominator is HAC is different from metallic wear, where we have the numerator WL by H usually, load times sliding distance divided by hardness. But here we have a impact strength or rupture mechanism to consider. So this is Ratner's equation, where it gives V is equal to K mu WL divided by HSE H hardness, ASH is rupture stress, and epsilon rupture strain. Then we have got in the same year, Lewis. He came up with an equation, the very linear equation, KWVT. KWVT is a simpler equation, and he got it from experimental relations. Here, K is the experimental wear constant, W is the load, V is the velocity, and T is the time. So here he brings in time. This is a new constant or new parameter compared to Ratner's equation. Then Lee, in 1970, came up with a nonlinear form of equation where he said V, where volume is equal to K, where constant, P to the power A, some exponent, P is the pressure, load per unit area, V is the velocity to the power D, and T is the time to the power C. So this is a nonlinear equation that Lee got from his experimental values. Anyway, these are some of the earlier work that we have seen. So it's important to discuss this before we go ahead with our own model. Then there are other nonlinear equations developed by Carr and Bahadur in 1974. The details are given below in the slide. One can look at this. They came up with the equation V is equal to K, again, P to the power X, V to the power Y, minus 2 to the T to the power Y, gamma to the power 3, minus Y plus Z, and E to the power Y minus X minus 3, into Cp by K to the power Z. So he introduced quite a few new parameters. He introduced surface energy, for example, and specific heat and thermal conductivity. I think these are well worth because these lead to melting wear, as we said earlier. Then is in 1979 came up with an equation. Came up with the equation of V by L. V by L is the wear volume per unit sliding distance, is a sum of pi squared d divided by 2L tan phi. Here again, P is the contact pressure, and D is the slider width, and L is the length of sliding or sliding distance, and phi is the angle between the shear plane of polymer and the horizontal axis. So this is again a new type of equation, but he got this from experimental values. Then Vishwanath and Bellow in 1995 came up with a linear equation, KW V is equal to KW WV T alpha divided by gamma. Here, they introduced again thermal constant, thermal parameters, alpha, thermal diffusivity, and gamma surface energy. So I think these two are well worth because gamma indicates a adhesive component, and alpha obviously is the thermal component because that leads to melting wear. They also came up with a nonlinear equation, which is V is equal to KW W to the power P V to the power Q T to the power T alpha to the power S e to the power minus 3 plus P plus R plus S and gamma to the power 3 minus 2P minus Q minus A, and then multiplied by Cp by K. Cp by K was also introduced to the power R minus Q. This component was also introduced by Bahadur. So this equation has got many new parameters or important parameters. Alpha, for example, alpha is a thermal parameter, thermal diffusivity. And E, of course, is the elastic modulus, gamma surface energy, and Cp is the specific heat, and K is the thermal conductivity. So these are the new types of equations. Now, I think here, alpha, they say, is the counter surface roughness. Usually alpha is thermal diffusivity, but here they have said it's counter surface roughness. So, and P, Q, R are the exponential parameters. So these are some of the earlier work that has been done, and we discuss this before we start our own model. Now, there have been some analytical approach also. Out of this, Kragelsky and Nepomansky in 1965 is a very important contribution. Here they say that the number of contacts is given by K4, sigma naught by sigma T. So number of cycles for fatigue during fatigue is a function of a ratio of sigma naught by sigma T. Sigma T is the applied stress, and sigma naught is the rupture stress, as we said earlier, and this to the power T. So this is a very important contribution and a novel idea. And from this, they have derived that the wear volume would be V is equal to pi A square delta by K4 sigma T by sigma naught to the power T. T is the experimental material constant. A is the contact area, and delta is the displacement while penetrating, and K4 is the wear constant. So these are some of the important contribution for analytical approach. Jain and Bahadur in 1980 also came up with a very useful linear equation where volume V is equal to K WL by S naught. Here V is, of course, the fatigue volume, K is the fatigue wear constant, W is the load, L is the sliding distance, and S naught is the of course S naught is of course the rupture stress, which is earlier other authors have used sigma naught, but here S naught is replacing H in the metal wear. This equation is very similar to metallic wear or Archer's metal wear, where it says V is equal to K WL by H, where H is the hardness and W is the load, L is the sliding distance. But here S naught is the different constant here, and this S naught they have explained in terms of many new material and surface topographic functions, parameters. So the Jain and Bahadur's equation is very similar to Archer's equation, but here they come up with a denominator S naught, which replaces the hardness in Archer's equation. And this has been shown in their paper given in reference 8 as a function of many material parameters and surface topographic parameters. They consider topography as an important factor in fatigue wear, which is understandable. Okay, so these are probably some of the important contributions made in the past in developing analytical and empirical wear modeling. Now, here we start our own model. The simplest abrasive wear model for polymers, which was developed by Ratner, which we discussed earlier, can be given as V1 by X. V1 we say is the abrasive wear volume, by X is the sliding distance. So abrasive wear volume per unit sliding distance is equal to K 1 by H. H is the hardness here, mu coefficient of friction, W load, and 1 by sigma naught epsilon naught. This equation has got three very important components. The first component is the surface deformation of an area of contact determined by the indentation. And that is probably given by 1 by H. Then hardness, of course, decides that. Then there's a relative motion opposed by the frictional force. So mu W is the frictional force. So this gives probably an indication of how much frictional energy is produced. Then the third one is the disruption of material at the contact surface involving the amount of work, sigma naught epsilon. So this is 1 by sigma naught epsilon is a work done on unit volume to disrupt the material or detach the material. So first thing in abrasive wear is to indent. Second thing is to plow it and produce wear flake, wear volume. And the third point is to detach it or disrupt the material. So this is a nice way of giving an equation. Now we use the same equation, but in Ratner's equation, K is a dimensional constant. So we make it non-dimensional. We call it K1, and we rewrite it as W by H. The second term is mu W by AR, and the third term is 1 by sigma naught epsilon. So the first term gives us an idea of the real area of constant. Second term relates to heat generation. And the third term, as we discussed, is the impact strength, which is correlated to abrasive, which decides or gives a measure of disruption of material or detachment of the wear flake that is produced by ploughing. So we use Ratner's equation, but in a modified form. Then we consider the influence of thermal parameters. Now the frictional heat which is generated, which is usually given by mu WV. Mu W is the frictional force and V is the velocity. So there is a frictional work done or frictional energy, and the sliding contact is shared between the rubbing bodies depending on their thermal properties and also whether the body is slow or fast moving. So whether the body is slow or fast moving is decided by a parameter called Becklet number, which is widely used in heat transfer, which is given by rho CVA by 2K2. K2 is the thermal conductivity, rho is the density, C is the specific heat, V is the velocity, and E is the contact area. So if the Becklet number is less than 0.1, we call it a slow moving contact. And if this is more than 5, we call it a fast moving contact. Many authors, including Archer, details are given in reference 10, have discussed this issue. And we quote from there that for stationary or slow-moving heat sources, when Becklet number is less than 0.1, then the contact temperature is given by Q divided by 4AK2. Q is the heat supplied at the contact, which is mu WV, and A is the contact area, and K2 is the thermal conductivity. But fast-moving contact, the equation is a little different, and obviously here the temperature will be time-dependent, and it is given by 2Q T to the power half divided by pi K2 rho C to the power half. Again, K2 is the thermal conductivity, rho density is specific heat, and Q is the heat flux, mu WV divided by pi a square. Now here, for proceeding further, we need to simplify this, and we define two new parameters, epsilon 1 and epsilon 2. Epsilon 1 is given by T divided by WV. T is the temperature, W is the load, V is the velocity. And epsilon 2 is T divided by W to the power root V. These are new parameters, and we use this in order to simplify our model. So we go ahead with this, and from equation 2 and 3, mu can be redefined, or mu can be written in terms of epsilon 1 and epsilon 2 for fast moving contact where L is greater than 5, mu is 1.97, epsilon 1, K2 root to the power alpha. Here alpha is the thermal diffusivity, K by rho C. Unlike in some of the previous past work, some of the authors have used alpha as roughness, but here alpha is the thermal diffusivity. And A to the power 3 by 2, A is the contact area or contact radius. And for slow moving or stationary bodies, L less than 0.1, mu is given by 4 epsilon 2 A to A. These are defined like this to ease our modeling, which will be clear as we go ahead. We'll show a little later that this epsilon 1 and epsilon 2 can be experimentally shown to be constant over a wide range of roughness values. So epsilon 1 and epsilon 2 would depend on only A, on how the contact radius varies. So this is a fairly useful parameter because it can be treated as constant, except that it will depend on A. Now, if we look back, equation 1, and eliminate mu from this in terms of the mu defined here, then we get the abrasive volume per unit sliding distance. We call it V1 dash because this is for single aspirated contact or high angle speed. So here we eliminate mu from equation 1 using the mu defined as above. We can write two equations. V1 dash by x equal to, for L greater than 5, V1 dash by x equal to 1.97 K1. K1 is a wear constant for abrasive wear. W square by HAR. W is the load per single asperity. H is the hardness, of the softer material here with the hardness obviously of the polymer, and AR is the contact radius, and epsilon 1 K2 divided by root alpha to the power A by A to the power 3 by 2 and multiplied by 1 by sigma naught epsilon naught. And for L less than 0.1, this reduces to 4K1 W squared by HAR epsilon 2 K2A multiplied by 1 by sigma naught epsilon naught. It is important to note here that the second bracketed terms in equation 4 and 5 refers to friction coefficient. And the third bracketed terms refers to impact strength. And impact strength, as we discussed before, is correlated to abrasive wear. So with this, we go ahead with our modeling. And there, having considered the effect of thermal properties, we'll consider the surface energy. As we said, the surface energy is important if we consider the adhesive component of the wear. When two clean and smooth surfaces are in contact, surface forces, surface molecular forces, van der Waals, ironing, and all that come into play. And the contact geometry is modified. Now, this has been discussed by many authors, but there are mainly two important models for elastic contacts. One of them is JKR, Johnson, Kendall, and Roberts, and other is DMT. Both these are more or less same, except that in JKR model, they consider the surface forces to act within the contact area, and DMT model, they consider the surface forces outside the contact area. And there have been a lot of discussion on this earlier. In earlier lectures, we have discussed this. We won't go into the details, but just will quote here the results of the JKR model. Now, if you look at JKR model, you can see that if there's a hemispherical asperity making contact with a smooth surface, then the load can be given by K3 A to the power 3 by R. K3 is the elastic, equivalent elastic constant given below here. I'm not repeating. Equivalent elastic modulus for two different materials in contact. And for adhesive contact, K3 A to the power cube A cube by R minus 6 pi gamma K3 A to the power 3 whole to the power half. Now, this is an important thing to note here, is that the load needed for producing the same contact is less in an adhesive contact. This is understandable because in adhesive contact, the surface molecular force adds to the applied load, and hence less force will be needed to make the same contact. This is a very important point to note. Now, for plastic contact, Ravinovich details have been given below. he came up with the following equations. Again, for plastic indentation, load is given by A pi AP square H, which is quite clear. Area multiplied by hardness. But for adhesive indentation, this is W is equal to pi AP square H minus 2 pi AP gamma cot theta 1. Again, the thing to note here is that for making the same area of contact, less load is needed in adhesive contact. Again, understandably, molecular forces adds to the applied load to make this difference. Now, it must be understood that the contact here is in a very small, we consider here a very small area of contact. And otherwise, this over the contact, the surface should be smooth enough and clean enough to produce this for the surface forces to act. So these are the two things, and these are the two important equations to remember. But for our abrasive wear model, I think equation 6 is more important than the other one. So with this equation 6, we go ahead with our model. And then we consider equation 6, or substitute equation 6 and equation 4 and 5, which have been developed earlier. And we have two new equations, 7 and 8. It's fairly simple algebraic manipulation. So I'm not going into the details of this. One can see the equation 7 and 8. Equation 7 is for high-speed contacts, L greater than 5. And equation 8 is for L less than 0.1. But here, what is important to note is that the second term here represents friction, as usual. This has been done in the equation 4 and 5 also. But the third, the last term in equation 7 and 8 represents fracture parameter. This is important here because when material is detached, new material, new surfaces are produced. And whenever new surfaces are produced, surface energy come into contact. Griffith's criteria, if we consider Griffith's criteria in elastic crack growth situation, then the condition for crack growth is given by pi A sigma square by E must be greater than gamma. A is the contact radius as shown in the figure, and pi A is of course the perimeter, and sigma square, sigma is the stress, applied stress. Now in the limiting case, this fracture parameter becomes pi equal to E gamma divided by pi A sigma dot square. Sigma dot is the yield stress. This is simply derived from the previous equation, taking this as 1. So this is a new parameter that we have added, considering the surface energy, because surface energy always relates to generation of new surfaces, and according to Griffith's criteria, it's a fractal parameter. So this we have added in the previous equation, and the equations have been developed for taking into account the fracture parameters. So we go ahead with this question 7 and 8, and then look at another important parameter, that is the sliding velocity. As we discussed earlier, that the contact of polymer rubbing against metal or any other surface, contact temperature will be may be high, depending on the rubbing speed and load. And if the temperature is fairly high, then will be melting wear. And this is why it is important to understand how coefficient of friction varies with sliding speed. Some of the experimental graphs are given on the right-hand side, and we can see that the friction rises to a peak and then falls. So there's a point of inflection. And at this point, we can expect thermal or melting wear. And this is why from the works of Nakatels and Tabor, we have two equations. For high speed, mu is given by kappa 1 by v to the power 0.5, and for low speed, mu is equal to kappa 2 by v. Kappa 1 and kappa 2 are dimensional constant, and these are experimentally obtained in the author's paper. It is now important to introduce these in our equations. Earlier, we defined mu in terms of thermal parameters. L less than 0.1, we said mu is equal to 1.97 epsilon 1 K2 by root alpha, it is about 3 by 2. And for L greater than 5, mu is equal to 4 epsilon 2 K2A. Now, we need to introduce these two equations, 9 and 10, into our earlier model to take into account the influence of sliding velocity. So let's see how we can do that. Now we go back to the Archer's equation and substituting mu is equal to K divided by V to the power 0.5 for high speeds contacts, and replace T, the time of contact, by A by V, A being the contact radius and V the velocity. We get K kappa 1 is equal to 1.25 Tm K2 rho C to the power half divided by H hardness to the power 3/4 W to the power 1/4. And this gives mu as Tm by W to the W root V K2 by root alpha A to the power 3 by 2. So this is a new definition of mu, which is in light of the effect of sliding velocity. And similarly for low speed contact, L less than 0.1, substituting mu is equal to kappa 2 by V, we can get mu is equal to Tm by Wv K2A. Now here there's one point to be understood. In Archer's formula, the heat generated at the contact produces different temperatures to different sliding bodies, to different bodies. Suppose we have got two bodies, A and B, and suppose their contact temperature is TA and TB. So we need to know what is the mean temperature at the contact. And the mean temperature at the contact is given by 1 by Tm equal to 1 by Ta plus 1 by Tb. This is a well-known equation. But when we consider the peak of the friction versus sliding velocity graph that we have just seen, yeah, we have seen this. And at the peak, I think we can replace the means temperature by Tm. That is why in equation 11 and 12, Tm is mean temperature, but it's taken as the melting point because we take the worst condition, that is at the peak of the friction versus sliding velocity curve. Now combining equation 1, 6, 9, and 10, we have got two new equations, equation 13 and 14. Now, these are valid for temperatures at or above melting point. Remember the equation 7 and 8 are valid for temperatures below melting point. So the equation shown here again is very simple. I will not go into the details, can be seen, but except to indicate that the second bracketed terms here refers to the coefficient of friction, which is in terms of melting point or melting temperature, Tm. And the last bracketed term in equation 13 and 14 are the fracture parameter. So it can be seen that equations are getting more and more complicated. So I felt that it's time to recapitulate what we have done so far. So what we have done is we started with Ratner's equation and written it in a modified form, V1 by X, that is abrasive wear volume per unit sliding distance is equal to K1. K1 is the wear constant for abrasive wear. W by V, mu W by AR, 1 by sigma naught epsilon. This we have discussed earlier. Then we take into account the thermal parameters. And there we have introduced two new parameters, epsilon 1 and epsilon 2. And we have written the coefficient of friction in terms of epsilon 1 and epsilon 2. So equation 4 and 5, the second bracketed term gives the coefficient of friction, but in terms of epsilon 1 and epsilon 2. Then we took into account the influence of surface energy, and we used Rabinovich equation, which gives W is equal to pi a square H minus 2 pi a gamma cot theta 1. This we have discussed because less load is needed when surface forces are operating. And combining this, we got two new equations. And there, the second bracketed terms remains the same, except that the last bracketed term refers to fracture parameter. And then we took into account the sliding distance of the sliding velocity, not sliding distance. And there we have got mu, or coefficient of friction, in terms of melting point of the material. So we got for L greater than 5, that is for fast moving contact, mu equal to Tm by W to the W root V, K2 by root alpha, A to the power 3 by 2, and for L less than 0.1, mu is equal to Tm by WV, K2A. Now using these, we have got two more equations. There is fairly similar to the previous equations, except that the coefficient of friction have been written in terms of melting point of the material. So this probably gives a brief idea of what we have done so far. Now we consider the multi-asperity contacts. So far we have been discussing the wear by a single asperity. Now we consider the roughness of the surface, meaning multi-asperity. Now, again, we discussed earlier that for abrasion, plastic indentation is more important, whereas for fatigue, elastic indentation is important. So we need to develop a plasticity condition to distinguish between the asperities, those indent the polymer elastically or plastically. The plasticity condition for hemispherical asperity is given in reference 7. The condition is modified for conical indental, is given here in equation 15 and equation 16. Equation 16 gives the condition for solving equation 15. We can find out the apparent critical displacement for plastic indentation. Now, these are converted into real or actual displacement by equation 16. Now, these two equations may be a little confusing, so I'll discuss this in a little bit in more detail in the next slide. But here, we need to have a look at the condition of contact. We take a rough surface, say Gaussian or any other surface, and making contact with a smooth surface. So here the roughness of both the surfaces have been imposed onto one surface. So we have got one rough surface, deformable rough surface, making contact with a hard, smooth surface. Now, this was the apparent and the actual contact area and the displacement has been discussed by Johnson in detail. So I'd like to discuss this in little detail here. if we consider two spherical elastic bodies in contact, initially there'll be a point contact, and then slowly there'll be a contact area developed. Now, if you look at the figure on the right-hand side, the Hertzian contact pressure is given by P, which is a semi-ellipsoid, semi-ellipse. We take the whole body as a semi-ellipsoid. And then P dash is a tensile force, because the surface force is acting in the opposite direction. And that's why we need less load. And that is given by P dash. So when the combined pressure is applied, then that is given by the pressure curve P minus P dash. So Johnson said the displacement due to the Hertz load is taken as an apparent displacement. Obviously, because when there is a surface forces are acting, then the displacement due to the Hertzian load is not the final displacement. We need to take into account the surface forces, which is acting in the opposite direction, the tensile force. So the displacement due to Hertz load minus the surface forces is the actual displacement. So this is the reason behind equation 15 and 16. Equation 15 have been developed for apparent contact displacement, critical displacement, and equation 16 have been developed for or converted to real or actual displacement. Remember, these two equations are modified for conical asperity, not hemispherical asperity. Okay, so with this, we proceed further, and then we need to take a probability function to combine all the effect of all the asperities. Not that all the surfaces are Gaussian, but for simplicity, we take here a Gaussian probability function and add up the effect of all the asperities. But before doing that, we non-dimensionalize the equation with the following scheme. So delta C, capital delta C is the non-dimensional critical displacement, delta C by sigma. So it is non-dimensionalized. All the displacements are non-dimensionalized with respect to sigma. Sigma is the standard deviation of the surface roughness. And then A is the contact area. H is the height, surface height. That is also non-dimensionalized with sigma. And A is delta cot theta 1. And V is the volume, volume, which is non-dimensionalized by N sigma Q. It is useful to remember a Gaussian distribution is given by phi z, z being the surface height here, and e to the power z minus z squared by 2 sigma squared divided by sigma 2 root 2 pi. Sigma is the standard deviation of the surface heights. Here we also used some non-dimensional factors or parameters. All the fractional components have been non-dimensionalized or written in terms of FHT, FLT, FHTM, FLTM, where H is the high speed, L is the low speed, T is the temperature lower than melting point, and Tm is the temperature at or above the melting point. Now here also we use three indices or three parameters. Adhesion index. Adhesion index theta is given in a modified form by K3 sigma by gamma. And abrasion index lambda is equal to H sigma by gamma. And fracture parameters phi is equal to gamma E by phi A sigma naught square. Now these have been done to simplify the equations because equations are fairly lengthy and to write it in a concise form, we need to use this shorter form. So here, as we said, that we have got 4 equations. One is where the high speed contact, L greater than 5, and contact temperature is less than melting point, and low speed contact, L less than 0.1, and temperature less than melting point. We've got 2 equations. And we've got 2 more equations for high speed contact, L greater than 5 and L less than 0.1. But here both the temperatures are above the melting point. Here one thing to remember is that the integration limits are delta Ca to infinity. That is because we are taking the plastic contacts. And we said that in the previous equations we have developed the critical displacement, delta Ca. So we need to find that and put it as a lower limit of the integral. And of course, we use the probability density function with it. But here, it can be seen that many non-dimensionalized or shorter form of the parameters have been used. For example, FHT, FLT, FHTM, FLTM, they're all friction written either in terms of epsilon 1, epsilon 2, or melting temperature Tm. And then there's a fracture parameter which we discussed here. And the limiting value of fracture parameter is 1, where the detachment starts or initiation of fracture. And then we have got abrasive and adhesive index. In abrasive index, the limiting value is 2, beyond which the roughness takes over. That means abrasion will be dominant than the fatigue. And similarly, for adhesion index, the limiting value is 3.2, beyond which the roughness will take over, and hence the effect of surface forces will be minimized. So these are the combined wear volume for different speed and temperature conditions. and for abrasive wear only. So in the next part, this is the first part. In the next part, we'll discuss the fatigue. So we end it here.